Hello, in this video we're going to derive or calculate how to generate double exponential data from scratch. And so specifically the R code, for those that want to cut right to it, there's 3 lines here and that's the only R code you'll need. No special packages. So if we want to generate a sample of size 100 with mu 25, and remember the mu has to do with where the center of the double exponential is, and the B is how spread out it is. You know, if the bigger this number is, the lower the peak and the fatter the tails. We generate random uniform 0-1 data, and then we plug it into this formula, and X is double exponential. Okay, so now we're going to derive how, or the theory behind why this works. So the density is f of x is equal to this function here. B is positive, x and mu are real numbers. So the CDF by definition is this. We're integrating from negative infinity to some number x. And then this is our density. But if we look at the plot of the density, I mean, whether we're below or above mu is going to pose a problem. So we have to have it in cases. So let's assume that x is less than mu. So that x is some point here, and we're integrating, we're finding the area under that tail. And so we're going from negative infinity to x, and here's our density. We make a U-substitution. U is equal to minus, it's really this exponent here. du is 1 over b dt. We plug this back in, we get this. Now the limits of integration, that goes to negative infinity, and that's just x, when we plug it in for t. And then I distribute the minus sign, which switches that. Antiderivative of e to the u is e to the u. Plug in our limits of integration. This piece makes it go to 0, so we're just 1/2 this. So that's part of the CDF when x is less than mu. Now we have to assume that x, the point where we stop, is greater than mu. Now if we look at this, so that means x is over here and we're integrating this whole area here. But we know this area is 1/2, so we can kind of skip that and just integrate from mu to x, and then we find that area. And that's kind of what we end up doing. So we go from x is greater than mu, so this is the start, but then we split this integral at mu. We go from negative infinity to mu and mu to x. And now by default we know this is 1/2, but we're going to derive it anyway just for practice. So then let's do a U-substitution with this exponent right here. du is dt over b. Now this u is not the same. We're thinking about these U substitutions separately. So u over here is again this. And notice that the mu minus t and the t minus mu switched. And that's because whether we're above or below mu makes a difference. And then the density has an absolute value sign. So we have to make those positive. So again, u is this exponent, du is minus dt over b. We plug this u substitution in here, this u substitution for this one, and then the antiderivative of this is 1/2 e to the u. I paused because my cat just jumped right in the chair beside me. Now she's leaning way over on the table. I just got to show you this. Oh, hi Ada. And Ada is, and so I imagine a paw is going to come in to attack my thing. So this right here is antiderivative is e to the u. Plugging in here's the limits of integration. Here it's minus e to the u, limits of integration. When we plug them in, that is 1, so we get 1/2. That makes it go to 0. And then we plug in these, we get this plus 1/2. Well, the halves make a 1 and we get minus. And so this is the second piece of the CDF. So now when we put them both together, the CDF function is defined like this. The two pieces dependent upon whether x is below or above mu. Now, so that's the first part. Now we have to find the inverse CDF. And there we're going to use the probability integral transformation. So this is the CDF, you know, and then at mu we know it's 0.5, right? But this CDF we know follows a uniform distribution. So if we let the f of x equal p, where p is a uniform variable from 0 to 1, and then we set it like this, and then we back solve for x, and then that's how we end up doing the you know, generating random variables from a double exponential. But notice that when we get a variable less than p, we're only dealing with this piece here, which is actually ends up being this piece, right? And if we generate a random number from 0 to 1 that's bigger than 0.5, we're only dealing with this up part right here. So we take it into two pieces. We have to think about it in two pieces. So the first one is that x is less than mu, meaning that we randomly generated a p less than 1/2. And now to me, this is the tricky part. And actually, I think it's so brilliant that notice that right now we're considered into two pieces. But if we go back to the code, there's no if ands or if else's, or it's just one line of code and it generates the data. So somehow, even though we're thinking about it in two cases, you know, somehow it's all going to come together. And that's what I think is so cool about this derivation. So we let p, which is a uniform 0-1 random variable, equal to our CDF. But specifically, we know that when we've generated that random number, that we're less than 1/2. You know, we're going to just deal with this piece first. That way we can just deal with this piece. So f of x is this, that's what I said. So now let's start back solving for x. Multiply by 2, we get this. Take the log of each side, we get this. Multiply up by b, add mu, we get this. Okay. Now this next step is where I think the part one of the creative step is. So we get this, but let's look at it piece by piece. So here's x equal mu. Now let's just focus on this b first of all. We need a plus b, but here's minus b. P minus 1/2. Notice, but all the p's are less than 1/2, so this is negative, and the sign function is either -1, 0, or 1, depending upon this. Since this is negative, the sign function makes it -1, which then multiplied makes it a positive b. So that's this piece. Now here we got the log, and over here we have 1, and then the -2 to 1/2 is -1, so 1 minus 1 is 0, goes away. -2 minus p is positive p, okay? So we're going to use this as our x, okay? And you'll see why in a second. Now, next we have to think about if we generate a p greater than 1/2, meaning that we're up here, which is this second piece of the CDF, okay? So that's why we do this. We set f of x equal to p, and f of x was this second piece, because we generated a uniform 0-1 random variable greater than 1/2. Okay, now let's start back solving for p. So I like to think about is subtract that over, subtract the p over, and then multiply by 2 to both sides, and then we end up with this. Now we take the log of both sides, and then multiply by b, and subtract that mu, but then multiply by -1, and anyway, you get this expression right here. Now we're going to do something with this. Remember, step one, creativity. similar to this. So let's go through this. X equal mu, now minus b. Now remember, the p that we generate is bigger than 1/2. So this is positive, which means sine of that is 1. So we stay with the minus b. And over here, we do this. So we have 1, and then the minus 2 times minus 1/2 is 1. So 1 plus 1 is 2. And then we get minus 2p. Okay? So this is exactly the same as this step. Oh, my cat's going to come in for an attack. So I'm backing her off with my left hand here. So this, look at this. This step is very similar to this step. Actually, they look identical except for this piece. So remember, p is less than 1/2, so this is positive. And here, p is greater than 1/2, so this is positive. So really, we could combine those and just put the absolute value around this piece, which then forces it to be positive no matter what p you get. And that's actually what we do. So the inverse CDF is mu minus b sine of this log of 1 minus 2 times this absolute value of p minus 1/2. And that's it. And that's actually how we solve for double exponential random variables. We generate normal 0, 1 random variables and plug them in here and just let it do its calculation, and that's what we do. Anyway, well, that's all I have for today. Hopefully you enjoyed that. I sure did. This is such a creative derivation. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.